Hi, so this is the lecture that I'm going to give on Monday, September 27th, 2021. It might go on a little past what that lecture actually ends on, but it's material that I do not have recorded from the fall of 2020. So I'm going to go ahead and do it. Let me just make sure. Hold on a sec, make sure I'm actually recording. Okay, I think I am. All right. So last class, I ended with talking about how you could use a distribution function to find an average. So we can use this type of function to get averages, but we can also get other things from a function like this. But getting back to where we were at the end of class last time, I said that the average height, for example, if you knew the height distribution, and I even showed a simple example where you could use the fraction of people at each height. Let's call that Fi, or Pi for probability at each height, because I talked about how that probability, that fraction becomes a probability when you have a large population. So the probability at each height times a particular height summed over all heights, okay? So this is the probability at each height multiplied by each height and summed over all heights would give you the average height, okay? Now, this is for what we call a discrete distribution. And a discrete distribution, it's like the one I showed you where you would have like finite intervals, like maybe you have, 2 inches or whatever it is, for whatever you wanted it to be for height. But generally in science, we often deal with what is called well, not yet. Actually, first I want to say that you could get the average height this way. If you wanted to get the average of, say, the square of the height, so the average of some other function of height, like, for example, the average square of the height. Why would you want to do that? Well, you wouldn't, but you'd want to get the square of the velocity. So I want to prepare you for that. You would have to sum up the probability times the square of the ith height over all heights, and that would give you the average of the square. So most often in science, we deal with continuous distributions. And by the way, you could put any function of height here, not just the square. It could be, 1 over height or something like that. Now, most of the time we're dealing with continuous distributions where you would have literally a continuous function of height like that. And then what happens to this average height sum here is the sum becomes an integral. And I think this is really where I was at the end of class last time. So we would have that the average height, instead of being a sum over all heights of the probability at a given height times the height, it would be that's probability at a height, not for an interval, but for a particular height, times the height integrated over all heights, which would be like 0 to infinity. No one's going to be taller than infinity or shorter than 0. So this would be, and I actually prefer writing it with the h first. And if you wanted the average square of the height, you would do the same thing, but you would put the square in there. Okay, so this would work for a speed distribution as well, if we knew what the speed distribution was. So then we would have, for a speed distribution, and of course what I'm talking about is for speeds of molecules, like in a gas sample. and I'm going to give you what that function is in a little bit, but the average speed would be, well, you can't have speeds less than 0 or greater than infinity, of v, p of v, dv. And actually this here is actually the probability that the speed is between v and v plus dv, because the probability at v is a single point. It would actually be 0. You have to have an interval, even if it's an infinitesimal interval, which is what this is. But anyway, that's a technicality. So what you would have here, and this p of v, this would be the speed distribution function. And then you could have the average of the square of the speed as v squared, p of v dv, averaged, integrated over all speeds. And what about the root mean square speed? Okay, well, you have to take the square root of the average speed. So it's literally the square root of this average v squared. So it's literally the square root of this integral. But, don't get excited. This is not so hard, because in the end, after you evaluate this integral from 0 to infinity, it's just a number. So you're just taking the square root of whatever that number comes out to be. All right. So here's the thing. We know from the kinetic theory, we know an expression for that average v squared, right? We know that this average v squared is 3RT over m. Okay, so that means that since we know the value of this average, and we know that that's the integral of v squared times the probability at a given v, what we can do is we can figure out what function works here. And what do I mean by that? Well, in other words, figure out what function, when plugged into this integral and multiplied by v squared integrated, gives you 3RT over m. Now, we're not going to do that. We're going to leave the mathematicians to do that. So that's for the mathematicians. This isn't math class, so some of the things we just tell you, this is, the mathematicians did this. We're not doing this, but I'm going to give you the result, all right? And the result is the function. So this P of V, we call this the Maxwell Boltzmann. It's that guy Boltzmann, he's very big deal. Distribution of molecular speeds. And actually, unfortunately, this is usually called F of V. It's not usually called P of V. I'm just telling you that the traditional way it's referred to. And it's 4 pi. Here's the molar mass over 2 pi RT to the 3/2 V squared e to the minus mv squared over 2 RT. Okay, and you never have to memorize that. You would always be given that if you needed to use it. So here's the thing, we're used to distributions being a bell curve, but this is not a bell curve. Why not? Well, a bell curve would be if you just had this part, e to the minus ax squared. So this is some bunch of constants here multiplied by v squared in the e to the minus a times, that in the exponent. We have this extra v squared here that's part of the distribution. This is the extra v squared is part of the distribution function. And what the v squared factor does is it skews the bell curve. So if I were going to draw a bell curve for you, Let's see, I'm going to put the middle of it over there, make this an even. So this be the same distance as that. Go up to here. So we'd have like, go up like that, and it would come down. Well, I didn't draw it that beautifully, unfortunately. Let me try a little better on that one. Now that's a pretty good bell curve, center about there. Okay, so this is a bell curve, but this is not what our curve does. What our curve does, the Maxwell Boltzmann curve, it rises faster and it falls slower. So it's not the best drawing. I'll try to make it a little bit better. Oh, I should have left it the way it was. Okay, so here it goes. It has a faster rise. It's f of v, the Maxwell Boltzmann distribution of speeds, and it has a slower decline. Okay, so that's the look of it. It's not quite a bell curve. So here is, I gave this slide out last time to you, this picture, although I believe the pies were missing. For some reason, that particular PDF file that I reproduced to give you did not have the pies in it, I believe. So let's take a look at this. And these speeds make no sense for a gas. So I'm just going to change this to 100, 200, 300 meters per second. I don't know what unit they did this in. This doesn't, these are pretty slow, it'd be pretty cold gas, but that's okay. So, you know, maybe this curve doesn't look too skewed to you, but if it were a perfect bell curve, right, this maximum is at 100, it would go down to 0 at 200, and it's not at 0 at 200. So it's a little bit skewed. Okay. So the first thing I have to say is, if it were a bell curve, the curve would equal 0 at 200, and it doesn't. Okay, and the second thing is, I'd like to ask, what's the total area here? And you know, that's a trick question, because these are probabilities, and so of course the total area is equal to 1. But I wanted to bring up the subject of area, because the total area is the total probability of having any speed. What's the probability of this gas having a speed greater than or equal to 200 meters per second? So that's the kind of information that knowing an average cannot possibly tell you, but knowing the Boltzmann distribution curve can tell you that. Because here, this area here, the red area, which would be given by this integral, right? It would be the integral from 200 meters per second to infinity of v squared times, you know, 4 pi, and these are just constants, over 2 pi RT to the 3/2 e to the minus mv squared over 2 RT dv. If you could evaluate that integral, you would know exactly what this fraction is. And actually, mathematicians have tables, and you know, there are ways of numerically and very easily numerically evaluating that integral. So that's not something we're going to do, but it's definitely doable, right? Definitely doable, but we're not going to do it. Okay. So then next thing I'd like to look at is the effect of temperature on that Maxwell Boltzmann distribution. And again, the curves that I managed to pick off the internet, it almost looks like that green curve is a bell curve, but it's slightly skewed. So you're just going to have to take my word for it. But this is what I want to point out here. So this shows the Maxwell Boltzmann distribution at 2 temperatures. The green one is the lower temperature, and T2 is a higher temperature. So let's take a look at a slow speed. So over here, this is about 200 meters per second. This is slow relative to most of the other speeds on this x-axis. So let's go up to here, okay? And what you could see is at this slow speed, the lower temperature, that's the green curve, the lower temperature has the greater probability. So it has a greater chance of moving at that slow speed at the lower temperature. And in contrast, let's pick 1500 meters per second. So at 200 Kelvin, the lower temperature has a greater, at 200, for 200 meters per second, the lower temperature has a greater probability. For 1500 meters per second, now you could see that the higher temperature curve has the greater probability. So at higher temperatures, molecules tend to move faster. At lower temperatures, they tend to move slower. Okay. Another thing you notice by looking at this curve that's very clear is that you have a much greater range of speeds. If we look at the full width at half maximum, that full width at half maximum is considerably greater, right? Go to the top, go to halfway to the top, and look at the width. Go to the top, go halfway to the top, and look at the width. That's the full width at half max is much greater at the higher temperature. So what to put that in simple words, there's a greater range of speeds. As temperature goes up. Okay. Another thing that we could look at is that let's consider the fraction of molecules, for example, that are moving greater than 1500 meters per second. So the fraction, I should write out what that is, I guess, fraction of molecules moving at speeds greater than 1500 meters per second. So if we go back to the curve here, here's 1500. Okay, so this black area here would be the fraction at the lower temperature, but this here so the red is the fraction greater than 1500 at the higher temperature, much greater. And then the black one is the fraction at the lower temperature, which is much smaller. And I'm going to just go back and look at that again. Right. Oh, I actually did it a little bit wrong. Let me erase some of that. Make it a little eraser. Made a big mistake there. Where's the eraser? Yeah, have to be on the right of that dotted line. Okay. So there's a greater fraction. So that would mean, of course, that, if you have a fraction of molecules moving faster than that speed at a greater fraction at a higher temperature, you're going to have greater kinetic energy on average, right? Well, you're going to have greater kinetic energy for those molecules that are greater than that speed. They'll have a greater kinetic energy. They'll be a greater fraction that are able to go over the barrier. Okay, so you're going to have a much faster reaction, for example, if those molecules were involved in a reaction. And really, you know, basically what this picture shows is, I mean, the average speeds are around the middle of these curves, and you know, there's a greater average speed as the temperature increases. I'll tell you where the average speed is in a minute, because first I want to tell you about molar mass. Then I'll talk about where is the most probable speed on these curves, where's the average speed, and where's that root mean square speed. But first, I'd like to talk a little bit about how the Maxwell Boltzmann distribution depends on molar mass. So I'm just going to label these because the colors are very nice, but I like them to be right next to what I'm talking about. So here are 4 different gases, from xenon to argon. These are all rare gases. So as you go from xenon to helium, you basically have a smaller molar mass, that M. And so it's a very similar situation. It's really mathematically identical to going to a higher temperature. So let me show you the distribution curve function again. Okay, so here you have the molar mass here is in the constant, but and temperature is in a constant as well on opposite sides of the fraction. But here is where it's really important, is in this exponent. Here you have molar mass here, so that's really molar mass, and you have temperature down here. So the important thing to gather from this is that when temperature increases, right, you're going to decrease the value of this exponent. The same thing happens when you increase the molar mass, decrease the molar mass. So decreasing the molar mass decreases the value of that exponent in precisely the same way as increasing the temperature decreases the value of that exponent. So you have really the same dependence. The same thing that happens as you increase the temperature happens as you decrease the molar mass. So that shouldn't be a surprise. Why isn't this working, huh? Okay, good. All right. Now, why is that 100% really? Oh, there we go. That's what we want. Okay, so the effect of decreasing molar mass, M, which is just capital M in the typed version of the distribution function, is the same as increasing T. So if you increase the temperature by, say, a factor of by 25%, you'll change this curve in exactly the same way as if you decrease the molar mass by 25%. And so you can see that as the molar mass increases, you have greater average speeds, just like when you have as it decreases, you have greater average speeds, just like as if you increase the temperature. You have a greater range of speeds, and you have shorter curves. Why do you have shorter curves? I didn't really address that in the temperature case, but if you have a greater range of speeds, whether it's due to a higher temperature or lower molar mass, well, you know, the areas of all these curves, all these areas have to be sum of the areas underneath them. All those probabilities have to add to 1. So they're shorter curves to maintain an area equal to 1 under each of them. Okay. And also you'll have a greater fraction of molecules. Let's see if I can get a little more space in here. Oh, well, I have to recopy that. And you have a greater fraction of molecules moving at higher speeds as you decrease the molar mass. Okay, so for example, fraction greater than, say, 1,000. You can see for helium, it's actually a rather large fraction. For neon, it's a pretty small fraction. For argon, it's basically non-existent fraction at those high speeds. Okay. So I wanted to go over something else, which is if we take a look at this curve, this is the graph that I've already shown you this graph, but I gave you a blank one of these to write on. So there are 3 what I call significant speeds that I refer to in this drawing. Given by these 3 lines here. So I'll label these like 1, 2, and since I don't have blue, what am I going to do there? Oh, I don't know what to do. 3. Oh, not too bad. Okay, so the first thing I want to say is that number 1, what speed does this represent? And honestly, I'm going to change these numbers because they don't make any sense for a gas. Okay. I should make these thousands, really. That would make even more sense. Okay, so 1 is what we call the most probable speed. Okay, so what does that mean? Well, it has the highest probability, right? It's right at the top of the curve, at the maximum. And in fact, since it's at the maximum, how would you find an expression for this V most probable? What you could do is you could take the Maxwell Boltzmann distribution function, V squared, it's a bunch of constants, times V squared e to the minus mv squared over 2 RT. Here's and you would take the function and differentiate it. You're going to find an extreme point. Differentiate this function with respect to V, of course. Okay, and then you'll set that derivative equal to 0. Now, when you differentiate this, these constants be constants times the derivative of this function, and this function is a product. So you'd have to use the product rule. And then you would set that equal to 0, and it doesn't matter what these constants are here because the constants would cancel with, cancel out. You divide both sides by constants. 0 divided by constants is still 0. And then you would solve for V. And this would give you the extreme points. Now, for this curve, there are actually 3 extreme points. What you would find is an extreme point at V equals 0, which would be a minimum. Then you would have an extreme point as V approaches infinity. That would also be a minimum. And then you would see another extreme point at some V you could solve for. That was not 0 and not infinity, somewhere between 0 and infinity. And that third V would be the most probable. Okay, so one of them would be a maximum, which you wouldn't have to prove that, but you know, just by looking at the shape of the curve, you know that at 0 and infinity, you have minima, and then you have one single maximum point. So that's how you could find an expression for that most probable speed. So that's the first one of these lines. Now, what about the second one? So here's the second one. So now, if this is your curve, I sort of exaggerate the skewedness a little bit more. So here's your most probable over here. The average is where you have equal probabilities, higher and lower. Now, because of the skewed distribution, the average is going to be a little bit, so this here is going to be the most probable. And this is going to be the average V, where you have equal areas. On either side of this particular, of the average V. Okay, because if you have equal probabilities at each side, then that's got to be the average. Okay, so it's a little bit shifted right. To the right of the most probable due to the skewed nature of the curve. All right. And now I'm going to tell you about the third one. Maybe you can guess what that is, because we've been talking about yet a different average, right? The average of the square. Okay. So the third one, go back, I just drew it even further to the right here, number 3. That is, I'm representing, that's actually the average of the square. Okay, so my question is, why is this a greater number? Why is the average of the square, why is it a greater value than the average, the plain old average, right? And you know, that's really the nature of the square function. Okay, when you do an average of a square, greater speeds count more, right? Because of the fact that the square increases faster as speed. So like when we just do a simple example, suppose you have 2 and 10 and you average them, right? So the average is 2 plus 10 over 2, which is 6. But now if you take 2 and 10 and you average the square, I'm sorry, this, I don't, really, this is the root mean square. It can't be the square. I'm sorry. 3 is the root mean square speed. So this is most probable. This is average speed. And this now is the root mean square speed. It can't have a different unit. So it's not really V squared, it's V squared square root. So that's when I was asking, why would the square root of V squared, why is this a greater value than the average V? I really should have said the root mean square. Obviously, V squared would have a greater value than the average V. But when you take the square root of it, you know, why doesn't it just come out to the average V? And so that's what I'm showing you here. If you have 2 squared and 10 squared, right? That's 104. If you take the square root of 104, you get, then you have to divide that by 2. That's 52. And now you take the square root of 52. So this is the average V squared. This is the square root of the average V squared, which is 7.2, and you can see that 7.2 is greater than 6. So it's not really a surprise that the average, the root mean square speed, I should say, is at a greater speed, is further to the right. So that's what those 3 That's what those three things are. Okay, so can we actually verify that this, well, actually we don't know what the expression is for the average speed. We can verify for the root mean square speed because we've been given that expression. But here is an exercise to figure out the average speed. Okay, so this is given the Maxwell Boltzmann distribution, find the average speed. I believe I gave this page out last time. Find the sample. So how would you use this distribution function now to find an average speed? Okay, so let me show you what's going on here. Okay, so let me just kind of give you a description of what you have to do here. Okay, so first of all, you know you have to do an integral. You know that the average speed is equal to the integral over all speeds of speed times that Maxwell Boltzmann distribution function. Okay, and we know what that is because that's given. We know V. Okay, then we have all these constants, 4 pi times m, that's the molar mass, that's what this is here, over 2 pi RT to the 3/2 v squared e to the minus mv squared. Looks horrible. But it really isn't because of what you're going to be given here. First of all, these constants will all come out to the front, okay? So our average V now will be a bunch of constants times v squared e to the minus mv squared over 2 RT dv. Now, here's the thing. If you notice at the bottom of that exercise, it gives you this important piece of information. You will need to know this integral. Now look at this. This integral has essentially been solved for you, okay? In other words, in math class, I might ask you, to figure out what this integral is, integration by parts or something like that. But that's not how we operate here in PChem, okay? You're given the fact that the integral of something, some variable cubed times e to the minus some constant. So a is a constant. All right, so e to the minus a constant times x squared dx, x cubed, I should say, times e to the minus ax squared dx. That integral from 0 to infinity is related to that constant a. So what we need to do is we need to look at this expression here, at this integral, because we're going to focus first on this part. Obviously, we can just multiply by the constants later on. But if you look at this part, okay, you say, all right, can I use this formula for this integral? What is A? What is X? Well, you could clearly see that the X is a V in this problem, all right? Here's a V here. V squared, just like you have an x squared here and you have an x cubed here. You have v, oh, shucks, I did that wrong. Ooh, I probably should start from the beginning here, but yeah, I noticed I left out this v here. Actually, I didn't do it too badly. All I did was I failed to multiply the v that you need for the average by the v squared in the distribution. All right, anyway, so now I corrected that, and you'll see that this v cubed goes with the x cubed. So what this really amounts to is trying to figure out what is that a. Let's get some more space here. So what is a in this integral? And if you look here, you see you have the molar mass over 2 RT. If you take e to the minus that times v squared, that's e to the minus a constant times v squared. So that a is m over 2RT. You know, this is kind of an important thing to be able to do. Like a lot of tables of integrals and things, they'll give you a whole sets of integrals, but they'll put it in a form like this, okay? And it may not exactly look like the form of your particular integral. Your integral might look something like this. So you have to say, okay, V is going to be X. So this X is really a speed. There's an X squared and the exponent is a V squared here. And then, okay, that A is going to be M over 2RT. So that means since this integral with the X and the A comes out to be 1 over 2A squared, this integral here, our integral, is going to be 1 over 2A squared. Can't have an X. Our integral is going to be 1 over 2A squared, or 1 over 2 M over 2RT squared. Okay, so if you put it all together, you'll have your constants. Don't forget, we still have these constants here. So we'll have, I keep needing more space. So our integral, our V, is 4 pi M over 2 pi RT to the 3/2 times, okay, 1 over 2A squared, 1 over 2 M over 2RT squared. Okay, that's what it is. So it remains now for you to simply figure out, to simplify it. You can't hand this in. This is the answer, but you must simplify it. And that's your job. What I recommend in a case like this, obviously you're going to have to flip this. It's going to end up being 2RT over M all squared. I recommend writing out all of those exponents. Okay, I find it easiest to do this. So for example, I would start out by writing, instead of M to the 3/2, I would write M to the 1/2 over 2 pi to the 1/2, R to the 1/2, T to the 1/2, right? And then I go on to this next part here, and you would have to and then it'll be easy to show the cancellation. So the point is that you have to show all your work here, and I'm the one that's reading it, and I need to know what you're talking about. So I don't want to see something with all kinds of crossouts in there, cross. Yeah, you need to show it so that a person reading it can understand, what it is that you're doing. Okay, so that's what I say you should do. Show your work and make it very clear what's going on. Okay, so show work, make cancellations very clear. Okay. All right. I have another special problem, which is very similar. I would like you to verify our formula for the root mean square speed. Okay, so again, here's the Maxwell Boltzmann distribution function. Now you're finding the average of the square. Okay, so you're finding the average of the square. So you're going to have to change the integral, right? Because remember, when you integrate a function of V, when you find the average of a function of V, you integrate that function times the distribution function over all possible values of V. So you're going to find the average V squared first. And then at the end, you take the square root. Okay, so each of those is a special problem. A special problem that you can do. I guess I'll collect it Monday. Okay, so let's see. So that's basically it for our diversion to the microscopic world. And the next thing I'm going to do is move on and talk about a little bit about real gases. Okay, so I guess we're starting real gases. And so the point is that gases are not always ideal. They do not always obey the ideal gas law. So, so a good question is, what's the evidence for this? I'll actually give you some data in a few minutes. And also, under what conditions does this happen? Is there any way that you can predict this sort of behavior? In other words, are there any equations of state that describe sort of like the ideal gas law, but for real gases? Okay, so I'd like to start with what I view as the ultimate consequence of non-ideal behavior of gases. And that ultimate consequence is the gas not being a gas anymore. So liquefaction. Okay. And when does this happen? Under what conditions? Well, I think everyone knows when gases liquefy, right? What's the first possibility? When the temperature gets low, right? So at low temperatures. But you can also increase the pressure, and high pressures will also cause gases to liquefy. So in both situations, both of these, gases, their molar volumes become very small. So the molar volume is just the volume of 1 mole. And we actually sometimes refer to that as Vm. It's just the volume over the number of moles. Okay. So when gases have small molar volumes, it means that the molecules are close together. And the particular, okay, so what happens when gas molecules become close to one another? Well, it depends on the particular gas, and it depends on how close they are. Let's see, so gases have small molar volumes. That means molecules are close together. So when these distances get small, and I'm talking about between molecules, the gas molecules do start to interact. The particular type of interaction depends on the gas. Depends on the particular gas. And also it depends on how close they are. Okay. And for example, here at low pressures, so when a gas is held at a low pressure, it does not have a particularly high molar volume, very low, doesn't have a particularly low molar volume. In fact, molar volumes are quite high. And this is where gases behave ideally. Okay. Then we have what I like to call moderate pressures, which really do vary from gas to gas. Moderate pressures. And these lead to attractions. So when these this starts to happen when molecules like a few molecular diameters apart. What are these attractions due to? Well, they're due to intermolecular forces, which if you had me for Gen Chem, I call these IMFs, intermolecular forces. These are, your dipole-dipole, your hydrogen bonding, and your dispersion forces. Same forces would exist in a gas, but only when the molar volumes start to get small, maybe a few molecular diameters apart, like I said. But what happens when you get to a realm of high pressures? And the definition of moderate and high really depends on the gas and how strong its intermolecular forces are. But at very high pressures, gas molecules actually repel each other. Because it's like, get out of my space. Two molecules cannot take up the same volume. So get out of my space. Okay. And so you could see that there is some complexity as to non-ideal gas behavior, that, you can't just make a blanket statement that gases will really attract each other. It's not true. At higher pressures, the dominant interaction is repulsion. So I'd like to talk first about the moderate pressure situation. So at moderate pressures, gas molecules attract. So we have some attraction. So this, like I said, starts to happen when there are a few molecular diameters apart. So I'm going to just draw a diagram here. And here I'd like to focus on this molecule. So this molecule is about to hit the wall. But it's got neighboring molecules, right? There's other molecules. And what are those other molecules doing is they are attracting this molecule to some extent. Okay, so the red arrows represent attractions to neighboring molecules. And what the effect is that what this leads to is, well, that black molecule is not going to hit the wall with as strong a force, and it's not going to hit as often because it's got this slight pull away from the wall. So it leads to fewer collisions with the wall and less forceful collisions. And both of these mean that the pressure is lowered. Okay, so what we have is a situation here where the pressure becomes smaller than the pressure predicted by the ideal gas law. What is the pressure predicted by the ideal gas law? Well, P ideal is nRT over V. So P is less than NIT over V. By the way, if P is less than P ideal, then the ratio P over P ideal is less than 1. And we actually give this ratio a name. We call this Z, the compression factor, or I usually call it the compressibility. Okay, so P less than P ideal, this is Z, will be less than 1. Okay. P less than nRT over V. So if I take that ratio, P over P ideal, that's P over nRT over V, which is PV over nRT, and that will be less than 1. Okay, so for a gas at moderate pressures where attractions dominate, so at moderate pressures where attractions dominate the picture, we have Z, which is P over P ideal, which is PV over nRT, is less than 1. So we could take this formula and write it as PV equals ZnRT. So you see, it's an altered law. I can't call it the ideal gas law anymore because it's not the ideal gas law. So for ideal behavior, that Z would have to equal 1, which of course would mean that the ratio of P over P ideal would equal 1. P equals P ideal. That would be ideal behavior. Okay, so you can see here that if this was 1, we would have the ideal gas law. Okay, but we don't. We have a different situation. So since the gas pressure, which we always call P, right? That is the actual pressure, okay? Sometimes it equals the ideal pressure, sometimes it doesn't. But as the actual gas pressure, P, is lower than predicted by the ideal gas law, we say that the gas is more compressible. And really, we mean more compressible than ideal. Or if you had two gases with two different Z's, and one was smaller than the other, the one with the smaller Z means more compressible. Why do we say that? Well, if a gas pressure is very high, it's hard to compress. If it's low, it's easier to compress. So the lower the value of Z, the more compressible the gas is, simply because the pressure is lower. Okay. All right. So as I've said, at low to moderate pressures, I'll go back to the summary here. Oh, I'll just write it again. What the heck? At really moderate pressures, I guess I'll reserve low for ideal. Moderate pressures, we have attractions dominate. P is less than P ideal. Z is less than 1. And remember, Z is P over P ideal. PV over nRT is less than 1 because that's Z. And we have PV equals ZnRT, where this will be less than 1. Okay, so I want to show you some data. And this is data. How far away is it? Oh, it's at another, let's see.